And we are back tackling the end of section 1. What? 2? Yeah, this would be 1.2c. Still talking about functions and their properties. We finished our last episode talking about symmetries and how to find odd or even symmetry algebraically. Both involved us substituting in negative x wherever it had an x and then looking at a result. Now we're going to talk about what our graphs are doing at their far reaches. We start by talking about horizontal and vertical asymptotes. Now, horizontal and vertical asymptotes are usually going to be found in rational functions, and if you remember, rational means fractions. So, things like this that you saw in Algebra 2. So what does it mean for something to be a horizontal asymptote? Well, I make mention of this when I teach Algebra 2, is that I really dislike the definition that a lot of Algebra 2 teachers give the word asymptote. They say that an asymptote is a line that a curve can't cross. But that's not always true. Um, it's always true for vertical asymptotes, but it's not always true for horizontal asymptotes. More on that to come. So a line y equals some constant number, we're calling it b, is a horizontal asymptote of a function if our graph gets close to that number as x gets really, really big or really, really small. Let me say that again. Technically, a horizontal asymptote is just a horizontal goal. If your graph gets incredibly close to that horizontal goal, if it gets incredibly close to that y value, as it stretches to the far left and you can't see what I'm doing, the far left and the far right, then that is known as a horizontal asymptote. So it's what's going on at the infinities. And yeah, there is some tricks to it. If the degree of the top of the function, meaning the numerator of the fraction, is less than the degree of the bottom, so if we have a larger exponent on the bottom, then our horizontal asymptote here on out would be represented as the HA, y equals 0 is our horizontal asymptote. Well, y equals 0 is the x-axis. So that happens when the exponent on the denominator is larger. Now, if the exponent, the degree of the numerator, is equal to the exponent of the bottom, then our horizontal asymptote can be found by saying y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Mr. M, it seems like you missed a third option. What happens if the exponent on top is bigger? Very good question, me. We'll get back to that. Now, the line x equals some number is a vertical asymptote. So y equals some number horizontal, x equals vertical. X equals a, which is just some constant, is a vertical asymptote of our graph. If our graph blows up to positive infinity, or can you say blows up to negative infinity? How about shoots? Shoots up to positive infinity or shoots down to negative infinity as x gets close to that x value. What a weird thing to say. Basically, if you are approaching an x value that usually is a no-no for a function, meaning it makes the denominator equal 0, and it doesn't matter which side you approach it from. If your graph shoots to one of the two infinities on either side of that value, then x equals that value will be known as a vertical asymptote. And I believe we've already talked about vertical asymptotes when we were talking about types of discontinuity. This would be known as an infinite discontinuity, again, because heading towards the infinities. So what's our trick? Well, I already said it, but it's usually the number that makes a denominator equal 0. And whatever that is a vertical asymptote. But you do have to remember that sometimes numbers that make the denominator equal 0 are removable discontinuities, and that happens when they cancel out of the top and bottom. So basically, if you're looking at a fully simplified version of a rational function, and you still have the ability to make the denominator equal 0, well, then that's where you're going to find those vertical asymptotes. If you used to have a number down there that's been canceled off, that's a removable discontinuity. Okay. Let's identify all of the asymptotes of these two rational functions. The way we're going to pull this off is by factoring anything that can factor. Where numerator is just x. That's simple. Nothing going on there. But our denominator, we're looking for the two numbers that multiply to -2 that add to -1. Sounds to be like -2 and +1. We factor because we're trying to see if anything's going to cancel out and create a removable discontinuity. Now, anytime we have a factor on the bottom that has the ability to equal 0, we're going to find vertical asymptotes. So this function has a vertical asymptote, the vase, vertical asymptotes at x equals 2 and x equals -1. This graph has two infinite discontinuities, vertical asymptotes. There they are. And what about the horizontal asymptote? Well, we look at the exponent on the top, look at the exponent on the bottom. The exponent on the top is not written, but it is a 1. So what we have here in this situation is the degree of the top being less than the degree of the bottom. So if we just head on up to our box right here, when the degree of the top is less than the degree of the bottom, then y equals 0. The x-axis is our horizontal asymptote. There. We found all three asymptotes of that function. All right, let's tackle part B. Switch colors for fun. We're going to factor anything that can factor. On the top, the numerator, we do have a GCF of x. There. Our denominator is exactly the same thing as it was before, so I don't have to rethink that. It's just going to be x minus 2 times x plus 1. Well, nothing's going to cancel. Nothing cancels at all. So we still have the same two vertical asymptotes. Our vertical asymptotes, also known as infinite discontinuities, are going to happen when x equals +2 and when x equals -1. But let's talk about that horizontal asymptote. Don't fall into this trap. The numerator of this function is not written in standard form. It's out of order. The largest degree, the largest exponent is always going to be the thing you're looking for. So if you wrote that numerator in the correct order, it would say -2x squared plus 3x. And it looks to me then that the degree of the top, 2, equals the degree of the bottom, 2. And if you go up to our little box up here, it says when the degree of the top and bottom are equal, your horizontal asymptote is going to be leading coefficient of numerator over leading coefficient of denominator. The leading coefficient of the numerator is -2 when it's written in standard form. And the leading coefficient of the denominator is 1. So there you go. Y equals -2 is the horizontal asymptote. That's how you identify your vertical and horizontal asymptotes. But remember that question that I asked myself a little bit ago. What happens if the degree of the numerator is larger than the degree of the denominator? Well, you don't have a horizontal asymptote. You don't have a vertical asymptote. Instead, you have something that we call an end behavior asymptote. We're not going to call it that just yet, but that's basically what it is. We get to talk about the end behavior of a function, and this is something that you tackled in Algebra 2. In Algebra 2, when you were talking about the end behavior of functions, you were looking at the exponent to figure out if your endings pointed the same direction. That was even degree polynomials. Or if your endings pointed opposite directions. This is odd degree polynomials. Well, what happens when it's not a polynomial is the question. What if it's a rational function? Well, that doesn't mean we just throw out the concept of end behavior. No. It's still possible. So how do we find the end behavior of a rational function? Well, end behavior is talking about the far left and far right. Again, the extremes as x approaches infinity. So if you want to figure out what's going on, what you have to do is imagine. I don't want you actually doing it. What you do is you imagine substituting in gigantic numbers for x. Numbers that get ridiculously close to infinity. I don't know, like 10 quadrillions, things like that. Absolutely massive numbers. You see, because when you start approaching these extreme values, only the terms with the highest degree actually matter. What do I mean by that? Okay, well, let's imagine you are somebody ridiculously rich. I don't know, like Bill Gates or something like that. You're walking down the street. Mind you, you're worth billions with a B. You're worth billions. You're walking down the street, and a $1 bill blows by you on the ground. Does it really matter? I mean, honestly, does it really matter if you stop to pick up that $1? I mean, you are one of the richest human beings on the planet. Does that $1 make much difference at all? No, let's be real. No, it really doesn't. This is the same basic idea. So check out this example. X to the fifth over x squared minus 2. As x gets ridiculously big, I'm talking like Bill Gates money big with a B, right? How much does this minus 2 really mean? I mean, in gigantic number to the fifth power, gigantic number squared. Oh, by the way, subtract 2. I mean, is it really making a difference? No. I mean, at the extreme values for x, this negative 2 means nothing. It just, and really the farther and farther away you go from x equals 0, the less it matters. So we can legitimately just cover it up and go, oh, towards the infinities, meaning to the extreme left and the extreme right, this thing is going to look like, it won't be directly equal to, but will look like x to the fifth over x squared. And that reduces to x to the third. So if you look over here at this graph, these solid lines, those are what this graph really looks like. The dotted line is y equals x to the third. And I'm hoping that you can see that our curve goes right through that thing, and it's nowhere near it here and there and there and there. But where does it get really close to the graph of y equals x to the third? It gets really close to that end behavior asymptote at the infinities. The farther left and farther right you go, the closer your curve will hug y equals x to the third. It's just really neat. So this is how you find the end behavior of a function that is not polynomial when these rules fall apart. What's going on in the middle? I'm gonna be real. That spaghetti doesn't bother me right now. I'm just talking about what's going on really far left and really far right. If you want to know what's going on towards the middle, we got to learn a bit of calculus. But that calculus is going to happen at the end of the year. So our final example of section 1.2. And it's just a matching question. Here we have 4 equations and 4 graphs. We're going to match them without knowing what the graph actually looks like. And we're going to do that using our end behavior. Meaning we're going to allow our x values to become gigantic. So for part A, as these x values get gigantic, this plus 1 really doesn't mean much. So this y is essentially equal to 3x over x squared at the infinities to the far left and the far right, which does reduce to 3 over x. What would that look like? Well, I mean, as x got really big, I'm hoping that we can all agree that if there was only $3 on the planet and all 7 and change billion of us had to share those $3, I'm hoping that we can all agree that we would get relatively $0. Essentially nothing. What that means is, to the far left and far right, we should be looking for a curve that's getting close to y equals 0. This one. It will be approaching this in behavior asymptote. The picture is just not big enough to do a really good job, but I mean, I'm hoping you can see that it was approaching, and it was approaching. For part B, same trick. At the extreme infinities, +1 really doesn't mean much at all. I mean, we're talking nothing. If I was the richest man on the planet, would one more dollar make me that much more richer? No. No. There's always a guy in the class that's like, yeah, it's always a guy. It's never a girl, it's always one of the guys. Stop it, men. You're making us look bad. Anywho, this y is going to be essentially equal to 3x squared over x squared at the infinities. And those x squareds would cancel at the infinities, giving us y equals 3. Y equals 3 is a horizontal line. So that is happening at graph I. Moving on to part C. We'll do that one in red. Part C, same trick. At the infinities, adding one more down here really doesn't mean much at all. And this will simplify. There are more x's on the top than there are on the bottom, specifically one more. So this will simplify to exactly 3x. That is a straight line with a slope of 3. There it is. I'm hoping you can see that if you could zoom out really, really far, instead of like zooming in, if you could condense the picture further and further and further, I'm hoping that you can see that that thing is just going to straighten out towards the infinities. Now, because of process of elimination, we already know that graph 4 matches part D, but just to really drive home the concept, we're going to prove it to ourselves. D. Towards the infinities, this +1, again, really does amount to a hill of beans. So essentially we're looking at 3x to the fourth over x squared, which would reduce to 3x squared. Our graph should be easily modeled by a quadratic to the far left and the far right. Oops, I should have made that dotted. Well, too late. I've already made the mistake. I might as well stick with it. There you go. You get the idea. So that's one way of identifying graphs, if it's a matching question on a test, without even knowing what the graph looks like. Knowledge is power, folks. And that's going to finish up 1.2.